Hello and welcome to lesson number 3. In this lesson, we'll be going over parent functions, and these are essentially the building blocks of every other function that you are going to see in mathematics. What these are, it's essentially a list of 20 some odd functions, and every other function will be either a transformation or a composition of these functions. So we'll go over function transformations in the next video. Function compositions will be unit 6, where we'll talk a little bit more about that. But these are the sort of basics or the building blocks of every other function that you will see in mathematics. Starting out, we've got the linear function. This is f of x equals mx plus b. This is slope-intercept form. If you really wanted it as its most basic, or at its most basic, it would just be f of x equals x. So your inputs and your output are the same. These form lines, hence the name linear equation with that root word line. They wrote it in slope-intercept form as if you change the m or b, you could have a positive line or you could have a negative line. You can shift this up or down, and we'll talk about how to do that in just a second. For now, what we want to focus on is the equation along with the domain and range. So for linear equations, your domain and range, again, domain is all real numbers. There's no issues plugging anything in. And your range is also going to be all real numbers, as you'll go from either the end behavior of as x approaches infinity, f of x approaches infinity, and as x approaches negative infinity, f of x approaches infinity, or the reverse of that, if you have a negative line. So your domain and range will both always be all real numbers. Absolute value functions, you will see it written like this. There is a piecewise breakdown of what this function is over here on the right. It's very, very similar to a linear function, except whenever you're given a negative input, say for example, -1, if you throw that into this function, instead of giving you -1 outs like this would, it'll give you +1 out. So it just turns all your negative values positive. Your domain would be -infinity to infinity, and your range will be 0 to infinity. So again, as we can see by the graph right here, these lines do continue out. And that happens for all of these graphs. Those go out forever. So our domain, there's not going to be any issues plugging in any numbers here. Range, again, since it turns all negative numbers positive, you'll just go from 0 to infinity. All right, square root function. And also, I do want to add a sort of side note as to, I guess, if you're wondering where all these pictures even come from. These are all functions. If you want to graph them on your own, you can sort of make a table of inputs versus outputs. If you have x and f of x, if I were to plug 0 in for x, then I plug in 0, the square root of 0 is 0, I would get 0 out for y. If I plugged in 4 in for x, for example, the square root of 4 is 2, I would get 2 out for y, or f of x. If I were to plug in 3, I think the square root is 1.9-ish, and that would be a point right here. You're essentially just getting a whole bunch of points and then connecting them with the line. That's what these functions all are. So the square root function, we can't plug in any negative numbers to a square root function, so we don't go anywhere in the negatives. Also, whenever we take a positive number and we take the square root of it, we're going to get another positive number. So our domain and range are both from 0 to infinity. Greatest integer function, we won't really need to be worried too much about this type of function, but they do show up from time to time. What this function does is it essentially just removes the decimal part of any number you put in. So for example, if I put in 1.5 as my input, it gets rid of the decimal and just says its output is 1. That's all that function does. We won't focus too much on these. Quadratic functions, these are very important. Again, they've got a little bit extra on this sheet. If you just want the bare bones function, it would be f of x equals x squared. That's actually this graph right here. Takes your input, squares it, gives you the output. Your domain for any quadratic will always be -infinity to infinity. Your range for this parent function should be 0 to infinity. However, we will talk in a second about transformations where we could, flip this and change the range. And some of the ranges on these can change as well. But for now, we're just looking at parent functions. So our range will be from 0 all the way up to infinity. Cubic function, another function with a exponent. And these look like this right here. So these aren't as commonly used as quadratics, but they are still good to know. And what's happening in this function is I take my inputs, say 1 for example, raise it to the third power and get my output. So when you take 1 and put it to the third power, that's 1. If I take 2 and raise it to the third power, that should give me 8, or a value way up here. Looks like the graph does cut that off. Our domain will be the same thing as the quadratics, negative infinity to infinity. No issues plugging any number into this. For our range in this case will be also from negative infinity to infinity. And that's because when I take a negative number and I square it or raise it to the second power, it's a negative times a negative, it'll give me a positive. So my outputs will always be positive for quadratics. But for cubics, if I take negative 2, for example, if I do negative 2 times negative 2 times negative 2, that should give me negative 8. I'll end up way down here. So our range will be all real numbers for the cubic function. All right, our rational functions, this is a parent function. This one doesn't really do justice to just how crazy some of these functions can get. Rational functions are all over the place. They won't always look like this. However, if you just have 1 over x, it will. And that goes for 1 over x, 2 over x, 7 over x, etc. What this function is doing is, essentially, it's really weird looking. It looks like we're approaching the y-axis over here and we're approaching the y-axis over here from different directions. What's happening here is, well, for one, if we plug in 0, we run into an issue. 1 over 0 is undefined. So we get what's called a vertical asymptote. So we'll never quite reach the y-axis. So let's look at the right-hand side of this equation. So over here. So what's happening over here is, let's say I plug in the number 1. Well, I'll get out the output 1, as 1 divided by 1 is 1. Well, let's say I plug in the number 2. What's going to happen is I get 1 over 2 as my output. That's 1/2, or 0.5, which is right here. Now if I plug in 3, I get 1/3, and so on and so forth. That pattern continues forever this way. However, once I plug in numbers smaller than 1, what ends up happening is my denominator becomes a decimal value, or a value greater than 0, less than 1. When I divide by that, my output sort of blows up. So let's say I plugged in 0.5. We'll just call it 1/2 to make it easier to write. I did 1 divided by 1/2. Well, this will end up, we'll use the keep change flip method. This will end up being 1 times 2, or just 2 as my output. If I plug in 1/2, I get out 2. If I plugged in, 1/10, I would get out 10. If I plugged in 1/millionth, I would get out 1,000,000. So as we get really, really, really close to the origin, this thing blows up. Same thing happens over here on this side, except the only difference is when I divide by a negative number, my output's going to be negative instead of positive. All right, so those are rational functions. Next up are exponential. And this is any number raised to the power of a variable, or the variable x in this case. What happens here is we do end up with a horizontal asymptote, and it is helpful to know the negative exponent rule here. So when you're working with an exponential function, unless you've got a transformation, you will never have a negative output. The reason for this is our negative exponent rule. If you need a review of that, it is this right here. So if you have a to the negative x, so some number raised to a negative exponent, this will be the same as 1 over a to the positive x. That's a little bit of a random throwback to an algebra rule. Just using this in an actual example with numbers. If I did 5 to the third power, that would be the same as 1 over 5 to the positive third power, 1 over 125. And so with exponential functions, it doesn't matter what the base is here. I guess it technically does. As long as it's a positive number, it doesn't matter too much what the value is. As we go more and more and more negative, this fraction right here, by the law of negative exponents, or the negative exponent rule, will become smaller and smaller and smaller. As we go larger and larger with the exponents, this thing sort of blows up really fast. If we had, for example, 5 to the x power, if x was 1, we'd have 5 and be around right here. If x was 2, we'd have 25, it'd be right here. If x was 3, we'd have 125, way, 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 way up here. So these graphs do blow up very fast. All right, your domain will be all real numbers. Your range, again, like I was just explaining, will be 0 to infinity. You won't have any negative outputs unless there's a transformation. All right. Logarithmic graphs are the opposite of exponential graphs. And we'll go over more of logarithmic functions in, I believe it's unit 7. However, just essentially what it's saying is it's the opposite of an exponent. Let's give a number example. So if I have log base 3 of 9, this entire value would be 2, as 3 to the second power is 9. So it's just asking you a question. It's saying, you know, this base raised to what power gives you this argument? In this case, it's 2. That's all logarithms are. When you graph them, they give you this sort of graph right here. And you'll never be able to put a negative number in this graph right here, or in this argument right here, as well. It's really a consequence of the negative exponent rule, that if you raise anything to the power to any power, it will never give you a negative value. It'll just give you 1 over whatever the positive version of that value is. So our range will be negative infinity to infinity, so we'll be able to hit all numbers on the y-axis, but our domain only goes from 0 to infinity. Those are the 1, 2, 3, 4, 5, 6, 7, 8, 9 basic types of functions. The rest of these functions are what are called trigonometric functions, and we'll work a lot with these later on in the semester. I'm not going to expect you to know exactly what all of these are now, but we do have a couple of them. We'll just go over them real quick. The first one is sine. So sine of x makes a wave, and this wave oscillates forever and ever and ever. Your domain goes from negative infinity. Range goes from -1 to 1. It's a consequence of the unit circle, which we'll talk about in the future. Cosine is really, really, really similar to sine. It's just, it hits the y-axis at, or the sine graph hits the y-axis at 0, 0, or the origin. Cosine graph hits the y-axis at +1. That's it. Right. Both of them are oscillating waves. Tangent. Tangent is a relationship between sine and cosine. Its graph looks like this right here. And this pattern repeats over and over and over and over and over again. And this one has a really, really weird looking domain. And tangent is sine divided by cosine. Whenever cosine is 0, we end up with an asymptote in the tangent graph. Right. So this pattern sort of repeats over and over and over again. And again, these functions are really, really beautiful, and we'll talk a lot about them in the coming videos. But for now, it's just good to know their shape and to know that they exist. All right, trig function number 4 is cosecant. This is sort of the opposite of sine. It's 1 divided by sine of x. It's got another weird looking graph too. If we scroll up to the sine function, whenever sine is 0, cosecant will have a asymptote, or it can't reach that value. As sine, or cosecant, is 1 divided by sine, and if sine is 0, we end up with 1 divided by 0, we end up with an asymptote. This structure right here, this weird looking parabola that's going up one way, down one way, up the other way, repeats forever and ever. And it's the same thing for secant. It's just secant is 1 over cosine instead of sine. So the asymptotes, or values it can't reach, are shifted. Right. Cotangent is just this tangent graph, but flipped. So it would be cosine over sine if you really wanted a actual definition for it. And again, all of these have really, really weird looking domains that we'll talk about in the future. All right, inverse sine. We haven't even talked about sine, so talking about arc sine would be a little bit redundant, but it has something to do with a unit circle and measurements on that unit circle. And so big side note here. But what sine will do is it'll say if we have an angle, let's say 45 degrees, we have a line with an angle of 45 degrees. It's like, what will this coordinate be right here? That was what sine would tell us. Arc sine would say, if we have this coordinate right here, what sort of angle would we need to make with the x-axis to get that? If that didn't make any sense, that's perfectly fine, but that's sort of the gist of how sine and arc sine are related. Same thing with cosine and tangent and their inverses. Arc sine actually just has this graph right here. Its domain never goes past -1 and 1, which is really similar to the range of sine. And its range just goes from -π/2 to π/2. And that has to do with the cyclical nature of sine itself. And again, we'll talk about all of that in the future. Arc cosine, opposite of sine, and arc tangent is the opposite of tangent. What we're going to do in the next video is we're going to use, again, not the trig functions, but we're going to use these basic functions up here, these parent functions, and try to determine what sort of shape random graphs are taking. So we'll look at that next video.